Alright, welcome to our next video for quantum mechanics. We're doing lesson number 7, which has two topics, but both sort of come from wave-particle duality. So hopefully everybody's okay with wave-particle duality. Let's move on and discuss these two topics. The first is matter waves. The matter waves is, change slides, there. So matter waves was mentioned in the video that you watched from the Perimeter Institute. Right? If we have, say, the momentum of a massless particle is h over lambda, well, why can't we just sub p as mv and solve for lambda and just simply say that any object with mass has its own associated wavelength, as long as it has velocity as well. Okay? And that's something that Louis de Broglie did, and they're called matter waves. Okay? And in the video you watched, you saw them constantly looking at bigger objects, not just fundamental particles, but atoms and molecules getting bigger and bigger and bigger, trying to see when quantum mechanics will break down, or if quantum mechanics will break down. This is the idea behind matter waves. And so that's just it. That's all there is to know about matter waves. It's a simple equation. And hold on. And let's start with our first example, which is on the back of your page. It says, what de Broglie wavelength, or what matter wave, is associated with a 0.1 kilogram ball moving at 19 meters per second? So we can take our equation and substitute the values, but because Planck's constant is so small, we get a wavelength on the order of 10 to the minus 34 meters. And remember, light itself is on the order of 10 to the minus 7. So this is extremely small. This is why you don't really see quantum effects in the everyday world, because your wavelength is so incredibly small, right? Imagine having a single slit that small. Well, we're so big we wouldn't be able to pass through it anyways. Okay. Next, what de Broglie wavelength is associated with an electron that has been accelerated from rest through a potential difference of 52 volts. So going back to this, electromagnetism, we can easily find out the velocity of that electron by looking at the work done by the parallel plates, where work equals charge times potential difference, and that's the change in kinetic energy. Assuming it starts from 0, we can solve for the velocity of the electron, which in this case is 4.27 times 10 to the 6 meters per second. Then we can sub that into our matter wave equation to see it has a wavelength of 1.7 times 10 to the minus 10. Now this is really cool, because this wavelength is a few orders smaller than light, and so it can resolve better. Right? This led to the invention of the transition electron microscope. Sure, we have optical microscopes, compound microscopes, but the resolution just meaning at what point are you still able to separate two objects as two objects, as opposed to just becoming one object, right? Light can do that pretty well, but electrons can do that much better, or their wave property anyways can do that much better. And so you can resolve things on a much smaller scale. All right, the uncertainty principle. You've probably heard about this before. Probably 80% of jokes in quantum mechanics are based on the uncertainty principle. Well, actually, I'm not too certain about that. Anyways, so it says you can't know the position and the momentum of an object with absolute certainty at the same time. Right? What it says is the uncertainty in x, so delta x, it's on the screen, but I'll write it here. The uncertainty in an object's position multiplied by the uncertainty in its momentum, and I should say that's in x, so we're analyzing this in one dimension, okay, equals, right, Planck's constant over 4 pi, not equals, sorry, it must be greater than or equal to Planck's constant over 4 pi. That means that the more you know about its position, for this to still be true, the less you must know about its momentum, and vice versa. So where does this come from? Well, it actually comes from wave-particle duality. Remember the most important laws of quantum physics? Rule number one, it's a wave. Unless you observe it, it's a particle. So let's look at a wave. Okay, and actually, let's go back to that previous equation. Let me just go back. Right here. The momentum of a particle is associated with its wavelength. So let's look at a wave. Here we have a wave. Now you could figure out its wavelength. Actually, let me make this a little bigger. So I'm going to draw a lot here. There we go. All right. So you can figure out its wavelength, right? Just right there. Crest to crest, trough to trough, right? Or somewhere in between to the exact same position and phase. And you can figure out its wavelength. And because you know its wavelength, you know its momentum. But where is it? You cannot identify its position anywhere on here. Okay, if you wanted to create a wave that looks like this, you can actually do that. Right? It's called a Fourier transform. Now I'm going to actually, it's a math concept that you don't learn in high school, so I'm going to link another video, which is a great video on YouTube that sort of explains what a Fourier transform is. But basically, what you can do is you can make any function with the addition of multiple sine waves. It's just based off of constructive and destructive interference. So if I have one wave here, I can add other waves to it. And these aren't perfectly to scale, right? And I can add other waves to it. And you might get something like this. Right? Now the more waves you add to it, these are terrible waves, but I said they're not to scale, the more accurate this will become, and it might even look something more like this. Okay, now if you put this all inside of a box, getting over to Schrodinger's cat here, but if you put it all inside of a box, there's your quantum object. Okay, so your quantum object exists somewhere in here. Okay, and there are different probabilities of where it would exist. But if you want to know more about its position and make this smaller, we need to add more possible wavelengths. And every wavelength we add is another possible momentum. So the more we try to learn about where it is, the less we know about what kind of momentum it can have. If you want to know more about its momentum, well, we'll start getting rid of all of these different wavelengths. Now you know more about its momentum. There's still some uncertainty. There's always going to be some uncertainty, but you know more about its momentum. But now you know less about its position. Okay, hopefully this makes sense somewhat. Basically, I get a lot of students saying, yeah, but maybe when our technology gets better, we'll be able to actually accurately measure its position and momentum. It's like, no. This is not an issue with technology. This is a fundamental property of quantum objects in nature. This is nature saying this is all you can ever know about a quantum system. You are not allowed to know more. Okay? So this is the idea behind the uncertainty principle. And I'm also going to post another video. We usually do a lab for uncertainty with a single slit. So I found a video of someone actually demonstrating that lab, which is really cool. So definitely check that video out too, so that you get a better understanding for what the uncertainty principle actually is. Okay, I'm going to make this small again. There we go. Okay. This explains the lab, but I'll let the video go ahead and do that. Well, okay, basically, if we have a slit, now this is a pretty wide slit, so if we send an electron through here, we don't know, well, this is the width of the slit is our uncertainty in its position. It could be anywhere in that slit. Okay, and you actually get this sort of curve, and this sort of explains its momentum. It's going to go up to here or down to there. It's going to be somewhere within that range. So it has a range of momentum in X. If you look at this last diagram, it shows you that. But if we make the slit smaller, right, our maxima, our central maxima, becomes bigger. So we know more about its position, less about its momentum. Okay, I'll let the video explain the rest because they got good animations. And there's lots of jokes if you want to read through here. So that's it for that lesson. Make sure you watch all the videos. It's pretty short, but if you felt bad about that, don't worry. Tomorrow's lesson is going to be more in depth. See you later.